Hello teacher, today I'm going to talk about the introduction and the background part of our research report. I am Sirat Çarkınkavas. So let's start with the introduction part. In introduction part, we're going to talk about memory wall, memory hierarchy and memory computing. For the memory wall part, memory wall is basically a technology, cannot catch the updates and improvements in processor technology, and latency and power consumption is very high. If we come to memory hierarchy and memory computing part, memory computing is a technology that keeps data in the system's memory instead of disks, and it minimizes data movement bottlenecks. My friend will explain data movement bottlenecks next. So basically a restricted number of pins on memory modules that cannot accommodate the bandwidth requirements and minimizes data movement bottlenecks. And near memory and in-memory computing, also known as basically a memory computing, reduces data bottlenecks. For introduction part, that's it. For the background part, it all started back in the 60s with some early idea. The logic has moved closer to the memory to reduce data movement. First appearance of near memory computing systems appeared in the early 19s, 30 years later than the first idea. Back in the early 19s, the first practical implementations appeared with near memory computing systems. There are some early prototypes included Execube, FPRAM, TerraCPM array, and VRAM. So basically, this is the background part. Thanks for listening to me.
Hello, Mr. El Haddad. I am Yusuf Selçuk Babacan, and I'm going to present the section Literature Review. To start off, what is the data movement bottleneck? Throughout the development of computer technology, CPU-related and storage-related technologies have developed independently from one another, both technologies experiencing exponential growth. Modern processors tend to be idle because they process the data received rapidly, causing being idle due to the limited data flow they receive. CPU processes information in a QVW, meaning the next bit of data should wait before the first calculation completes, limiting the data transferred. This whole concept is called the data movement bottleneck. Okay, so how does memory computing work? In-memory and near-memory computing are developing architectures designed to overcome the latency and power bottleneck caused by moving vast amounts of data between memory and processors. As the name suggests, in-memory computes inside memory areas like SRAM and ReRAM by modifying cell properties, while near-memory places logic adjacent to the memory like in the same package or stack. Okay, so to sum up, how do in-memory and near-memory computing reduce data movement bottlenecks? In-memory and near-memory computing reduce data movement bottlenecks by moving computation closer to or directly inside the memory, reducing or eliminating the energy-intensive and slow process of moving data between memory and the central processing unit. The computation process takes place next to the memory. This removes the need to move the data over the data bus to the processor. This process reduces the distance and the energy required for communication while still holding traditional DRAM rewrite capabilities. Thank you for listening to me.
My name is Boran Sir, and I will be talking about the potential vulnerabilities of near memory computing and in-memory computing. Starting off with near memory computing, the first problem that we're going to have is the cache clearance problem. The cache clearance problem is the difficulty of keeping data consistent between both the CPU and the near memory units, meaning that the data isn't up to date or what it should be in one of these, and this can incredibly reduce performance. And then we have the virtual memory problem. The virtual memory problem is when the NMC units have a hard time accessing the data because they lack the hardware in order to translate virtual addresses into physical ones. Then we have the programming model problem. The programming model problem is that it's hard to decide which parts of the program should be moved to the near memory without making the software too complex. Then we have the data mapping problem. The data mapping problem is when the data isn't stored close enough to the processing unit, and this just causes the system to lose all of its speed advantage. Moving on to in-memory computing, we have two main problems, one of them being limited programmability, and it's basically that the IMC, the in-memory computing systems, they're usually either very fast at a very specific task, or they're slower and less efficient, but they're more versatile, being able to do multiple different tasks. And then we have their dependency on the memory technology that they're using, because the in-memory computing processors, they're only as good as the memory technology being used with them, because they cannot surpass the speed of the memory technology being used. So any sort of disadvantage that the memory technology that's being used has will automatically be inherited to the in-memory computing processor as well.
Hello everyone. In this section, I will talk about challenges in near memory and in-memory computing architectures. The speaking part will be like summary. If you want to get more information, more detailed information, you can check my report also. So let's start. What do we have as problems? We might have problems with cache consistency. To solve it, we should divide memory into restricted areas, or we can use hardware based solutions to track the updated addresses. These solutions will uh, these solutions will reduce the traffic memory. So one of the most critical recommendation in our study is energy efficiency. Instead of adding massive accelerators, we should repurpose existing SRAM banks to perform logical operations direct on bit lines. By doing this we are achieving a massive increase in energy efficiency. Now let's talk about security and sustainability. The fact that data never leaves the memory naturally protect us from external bus vulnerabilities. By performing encryption directly within the memory, we can provide top-tier hardware level security. Furthermore, in the future architectures, we must focus not just on raw speed, but on compute efficiency per watt. This will extend hardware lifespan, reduce electronic waste, and lower our carbon footprint, helping us build more sustainable, green technologies for our world. And these days, all the world care about the sustainability, and they are trying to do something about sustainability. So this is the one of the most important things in our daily life. That was it. Thank you for listening.
To sum up our presentation, I will explain the memory wall challenge and the future of computer architecture. Let's start with the problem. Traditional von Neumann architecture struggles heavily with modern artificial intelligence and big data workloads. Moving data back and forth consumes ridiculous amounts of energy and heavily restricts speed. This severe bottleneck is what we call the memory wall. While near memory and in memory computing offer great solutions by bringing computation closer to the data, they are not flawless. As you can see on the slide, we still face integration problems like cache coherence and programmability. To fix this, the answer lies in hybrid approaches like INMC, combining the strengths of both IMC and NMC. Instead of adding large external accelerators, designers are repurposing existing SRAM to the computations directly inside the memory. This allows fundamental logic operations to be executed instantly, saving massive energy with minimal hardware cost. IMC also provides natural cybersecurity. Normally, data traveling on a bus is exposed to side-channel attacks. However, because IMC performs encryption inside the memory array, sensitive data never leaves, making it invincible against external attacks. Moving forward, the tech industry must prioritize environmental friendly practices, not just faster processors. Reducing data movement directly translates to a reduced carbon footprint, which is essential for global sustainability, the core of green AI. These approaches extend hardware lifespan and prevent electronic waste. In conclusion, the future of computer architecture does not lie merely in developing faster CPUs. The true future lies in completely breaking down the infamous memory wall. Thank you for watching.